Welcome, dear listener, to xnoesis. Find a comfortable position. Allow the weight of your body to settle, to release into the surfaces that support you. Let the sounds of your environment fade into a gentle, indistinct hum. There is nothing for you to do now but to listen, to allow your mind to drift on the currents of thought as we embark on a journey. Today's topic for our dive is Reality is Not What It Seems, The Journey to Quantum Gravity, book by Italian physicist Carlo Rovelli. During my entire research life, a question has surfaced time and again, spoken in quiet moments by friends or posed with bright curiosity by strangers. They ask me to explain what is happening at the very edge of our understanding, in the quiet, focused world of quantum gravity research. They wonder, with a sense of awe, how it is even possible for the human mind to study new ways of thinking about space and time, to question the very stage upon which our lives unfold. Over and over again, I have been asked to write a popular account of this research, to open a small window into this strange and beautiful landscape. And for a long time, I hesitated. While books on the grand sweep of cosmology or the intricate mathematics of string theory abound, a book describing the patient, collective search for the quantum nature of space and time, and on the quiet revolution of loop quantum gravity in particular, did not yet seem to exist. I wanted to concentrate on the research itself, on the silent dialogue with the equations and the ideas. But some years ago, after completing my technical book on the subject, a feeling began to grow within me. I felt that the collective work of so many scientists, laboring in quiet corners of the world, had moved the topic to a stage of maturity, a stage where its story could be told. The landscape we are exploring is truly enchanting, filled with a quiet, profound beauty. Why, I asked myself, should we keep it hidden? But still, the project remained a distant thought, a potentiality, because I could not see the book in my head. The central challenge felt immense. How does one explain a world without space and time? How do you paint a picture when the very canvas has dissolved? The answer came to me one night in 2012, during a long, solitary drive from Italy to France, the world outside the car a dark, flowing river of night. I realized, in a moment of quiet clarity, that the only way to explain these ongoing modifications to our deepest notions of space and time was to tell the story from its very beginning. We had to start with the first glimmer of the idea, with the ancient thinkers who first dared to imagine the world as a finite collection of grains. We had to trace the thread from Democritus all the way through the grand revolutions of physics to the modern-day quanta of space. After all, this is how I myself came to understand the story. It is a continuous, unbroken line of inquiry, a conversation spanning millennia. As I drove through the darkness, I began to design the entire book in my mind, each chapter connecting to the next, the ideas flowing one into the other. I grew increasingly excited, feeling the structure take shape, until the sudden, sharp wail of a police car's siren pulled me back to the present moment, telling me to pull over. I had been so lost in thought, I was driving far, far above the speed limit. The Italian policeman, approaching my car, asked me politely, with a hint of concern, if I was perhaps crazy to drive at such a speed. I tried to explain, stumbling over my words, that I had just found an idea I had been seeking for so long. The policeman looked at me, then at his partner, and after a moment that stretched into a small eternity, a smile touched his lips. He let me go without a ticket, and with a simple, kind wish. Good luck with the book. This is that book. This book was written and first published in Italian at the beginning of 2014. It was my attempt to capture the story that had unfolded in my mind on that long night drive. Shortly afterwards, a new opportunity arose. I wrote a few articles on fundamental physics for an Italian newspaper, shorter pieces meant for a broader audience. A prestigious Italian publisher, Adelphi, saw in these articles the seed of something else and asked me for an extended version to appear as a small booklet. This was the origin of the short book, 7 Brief Lessons on Physics. To my immense and continuing surprise, that little book became an international bestseller, and it opened a beautiful, unexpected channel of communication between me and so many wonderful readers all over the world. The 7 lessons were thus written after this book, and to some extent they are a distillation, a synthesis of some of the deeper topics you will find here. So if you have read 7 brief lessons on physics, and you felt a desire to know more, to journey deeper into the strange and beautiful world that book only sketched, here you can find that deeper dive. Here we can take our time. Now, a word of caution, a gentle reminder. While the account of established physics I give here is presented from the peculiar perspective in which I understand it, it is largely uncontroversial. It is the shared landscape of our scientific heritage. However, the part of this book that describes the current research in quantum gravity is, by necessity, my own personal understanding of the state of the art. This is the frontier. This is the region at the boundary between what we have understood and what we do not yet understand, and it is still far from achieving a comfortable consensus. Some of my physicist colleagues will agree with what I write here. Others, with equal passion and intelligence, will not. This is true for all presentations of ongoing research at the frontiers of knowledge, but I prefer to state it upfront and clearly. This is not a book about certainties. It is a book about the adventure itself, the quiet, thrilling adventure of moving towards the unknown. As a whole, think of this not as a textbook, but as a travel book. It describes one of the most spectacular journeys that humanity has ever taken. A journey out of our limited and parochial views of reality towards an increasingly vast and increasingly strange understanding of the structure of things. It is a magical journey, a journey out of our common sense view of the world, and it is a journey that is far, far from complete. We are, as a species, obsessed with ourselves. We study our history, our psychology, our philosophy, our gods. So much of our knowledge revolves around the human experience, as if we were the most important thing in the universe. I think, perhaps, I have always liked physics because it opens a window through which we can see further, beyond the confines of our own immediate concerns. It feels like a breath of fresh air entering a long closed house, and what we see out there, through that window, is constantly, beautifully surprising us. We have learned a great deal about the universe, and in the course of the centuries we have come to realize just how very many wrong ideas we had. We thought that the Earth was flat, a static, unmoving plate at the center of everything. We thought the universe was small, intimate, and unchanging. We believed that humankind was a breed apart, without kinship to the other animals that share our world. We have since learned of the existence of quarks, the fundamental constituents of atomic nuclei, of black holes where gravity becomes so strong that even light cannot escape, of particles of light themselves, the photons that carry images of the world to our eyes, of waves of space, ripples in the very fabric of reality, and of the extraordinary, intricate molecular structures that dance within every single cell of our bodies. The human race is like a growing child who discovers, with wide-eyed amazement, that the world consists not just of his bedroom and his playground, but that it is vast, and that there are 1,000 things to discover, and innumerable ideas quite different from those with which he began. The universe is multiform and boundless, and we continue to stumble upon new, unexpected aspects of it. And a curious thing happens. The more we learn about the world, the more we are amazed by its variety, its beauty, and its underlying simplicity. But the more we discover, the more we understand that what we don't yet know is vaster still than what we know. The more powerful our telescopes become, the stranger and more unexpected are the heavens we see. The closer we look at the minute detail of matter, the more we discover of its profound and layered structure. Today, our gaze reaches almost to the Big Bang, that great primordial explosion from which, 14 billion years ago, all the galaxies were born. But we have already begun to glimpse something beyond the Big Bang itself, a hint of a time before time. We have learned that space is curved, a flexible fabric rather than a rigid stage. but we already foresee that this same space is woven from something more fundamental still, from vibrating quantum grains. Our knowledge of the elementary grammar of the world continues to grow. If we try to put together what we have learned about the physical world in the course of the 20th century, the clues point towards something profoundly different from what we were taught at school. An elementary structure of the world is emerging, a world generated by a swarm of quantum events, a world where the familiar notions of time and space do not exist in their usual sense. In this vision, quantum fields draw space, time, matter, and light, exchanging information between one event and another. Reality is not a static stage, but a network of granular events. The dynamic which connects them is probabilistic, a dance of chance and necessity. And between one event and another, space, time, matter, and energy seem to melt away into a shimmering cloud of probability. This strange new world is slowly, patiently emerging today from the study of the main open question posed in fundamental physics, quantum gravity. It is the problem of coherently synthesizing what we have learned about the world from the two major discoveries of 20th century physics, general relativity and quantum theory. To quantum gravity, and to the strange, beautiful world that this research is slowly unfolding, this journey is dedicated. This experience, this monologue, is intended as a live coverage of the ongoing research. What we are learning, what we already know, and what we think we are just beginning to understand about the elementary nature of things. It starts from the distant origin of some of the key ideas that we use today to order our understanding of the world. It describes the two great discoveries of the 20th century, Einstein's general relativity and quantum mechanics, trying to put into focus the core of their physical content, the deep shift in perspective they demand. It tells of the picture of the world which is emerging today from research in quantum gravity, taking into account the latest indications given by nature, such as the confirmation of the cosmological standard model obtained from the Planck satellite, and the failure at CERN to observe the supersymmetric particles that many had expected. And it discusses the consequences of these ideas, the granular structure of space, the disappearance of time at the smallest scales, the physics of the Big Bang itself, the origin of the mysterious heat of black holes, all the way to the fundamental role that information seems to play in the very foundation of physics. In a famous myth, related by Plato in the 7th book of his Republic, some men are chained at the bottom of a dark cave. They can see only the shadows cast upon a wall by a fire behind them. They think that this play of shadows is reality. One of them frees himself, leaves the cave, and discovers the light of the sun and the wider world. At first, the light, to which his eyes are unaccustomed, stuns and confuses him, but eventually he can see, and he returns, excited, to his companions to tell them what he has seen. They, of course, find it hard to believe. We are all, in some sense, in the depths of a cave, chained by our ignorance, by our prejudices. Our weak senses reveal to us only shadows. If we try to see further, we are confused. We are unaccustomed. But we try. This is science. Scientific thinking explores and redraws the world, gradually offering us better and better images of it, teaching us to think in ever more effective ways. Science is a continual exploration of ways of thinking. Its strength is its visionary capacity to demolish preconceived ideas, to reveal new regions of reality, and to construct novel and more effective images of the world. This adventure rests upon the entirety of past knowledge, but at its heart is change. The world is boundless and iridescent. We want to go and see it. We are immersed in its mystery and in its beauty, and over the horizon, there is always unexplored territory. The incompleteness and the uncertainty of our knowledge, our precariousness, suspended over the abyss of the immensity of what we don't know, does not render life meaningless. It makes it interesting, and it makes it precious. I have crafted this experience to give an account of what for me is the wonder of this adventure. I've done so with a particular listener in mind, someone who knows little or nothing about today's physics, but is curious to find out not only what we know, but also what we don't yet understand about the elementary weave of the world and where we are searching. And I have done it to try to communicate the breathtaking beauty of the panorama of reality, which can be seen from this unique perspective. I've also done this for my colleagues, fellow travelers dispersed throughout the world, as well as for the young women and men with a passion for science, eager to set out on this journey for the first time. I've sought to outline the general landscape of the structure of the physical world, as seen by the double lights of relativity and of quantum physics, and to show how they can be combined. This is not only an act of divulgation, it's also one which articulates a point of view in a field of research where the abstraction of the technical language may sometimes obscure the wide-angle vision. Science is made up of experiments, hypotheses, equations, calculations, and long discussions. But these are only tools, like the instruments of musicians. In the end, what matters in music is the music itself, and what matters in science is the understanding of the world which science provides. To understand the significance of the discovery that the Earth turns around the Sun, it is not necessary to follow Copernicus's complicated calculations. To understand the importance of the discovery that all living beings on our planet have the same ancestors, it is not necessary to follow the complex arguments of Darwin's books. Science is about reading the world from a gradually widening point of view. This monologue gives an account of the current state of the search for our new image of the world as I understand it today. It is the reply I would give to a colleague and friend asking me, "So, what do you think is the true nature of things?" as we walk along a quiet shore on a long midsummer's evening. Our journey begins in Miletus, a bustling city on the coast of what is now Turkey, 26 centuries ago. Why begin a book about quantum gravity with events, people, and ideas so ancient? I hope the listener, eager to get onto the quanta of space, will not hold this against me. For it is always easier to understand ideas by starting with the roots from which they have grown. And an important number of the ideas which turned out to be the most effective for understanding the world originated over 2,000 years ago. If we briefly retrace their birth, they become clearer. And the later steps we must take turn out to be simpler, more natural. But there is more. Certain problems that were first posed in antiquity continue to be crucial to our understanding of the world today. Some of the most recent ideas about the structure of space utilize concepts and address issues that were introduced then. In speaking of these distant ideas, I am putting onto the table questions which are going to be central to quantum gravity. This makes it possible, when we later arrive at the heart of the matter, to distinguish between the ideas which go back to the very origin of scientific thought, even if they are unfamiliar to us, and those which are radically, profoundly new. The connection between the problems posed by the scientists of antiquity and the solutions found by Einstein and quantum gravity is, as we shall see, surprisingly, beautifully close. According to tradition, in the year 450 BCE, a man embarked upon a ship traveling from Miletus to Abdera. It was to be a crucial journey for the history of knowledge. The man, whose name was Leucippus, was likely fleeing political turmoil in Miletus, where the aristocracy was violently seizing back power. Miletus had been a prosperous and flourishing Greek city, perhaps the principal city of the Greek world before the golden age of Athens and Sparta. It had been a busy commercial hub, dominating a network of almost 100 colonies and commercial outposts stretching from the Black Sea to Egypt. Caravans from Mesopotamia and ships from all over the Mediterranean arrived at Miletus, and with them came not just goods but ideas. Ideas circulated in the air, in the markets, in the agora. During the preceding century, a revolution in thinking which would prove fundamental to humanity had taken place in Miletus. A group of thinkers had reformulated the very way questions were asked about the world, and the way answers were sought. The greatest of these thinkers was Anaximander. From time immemorial, men had asked themselves how the world had come into being, what it was composed of, how it was ordered. For thousands of years they had given themselves answers which all resembled one another, answers which referred to elaborate stories of spirits, deities, and mythological creatures. From cuneiform tablets to ancient Chinese texts, from the Bible to the myths of the Sioux, it was all a colorful but monotonous flow of plumed serpents and great cows, of irascible or kindly deities who create the world by breathing over abysses or emerging out of a stone egg. Then, at Miletus, Thales, his pupil Anaximander Hecataeus and their school, found a different way of looking for answers. This immense revolution in thought inaugurated a new mode of knowledge, signaling the first dawn of scientific thought. The Milesians understood that by shrewdly using observation and reason rather than searching for answers in fantasy or ancient myths, and above all by using critical thought, it is possible to repeatedly correct our worldview and to discover new aspects of reality hidden from the common view. Perhaps the decisive discovery was that of a different style of thinking, where the disciple is no longer obliged to respect and share the ideas of the master, but is free to build on those ideas, without being afraid to discard or criticize the parts that can be improved. This is the key to all subsequent development of philosophical and scientific thinking. From this moment on, knowledge begins to grow at a vertiginous pace, nourished by past knowledge, but at the same time by the possibility of criticism. This new approach to knowledge worked quickly and impressively. Within a matter of a few years, Anaximander understood that the Earth floats freely in the sky, unsupported, and that the sky continues beneath the Earth. He deduced that rainwater comes from the evaporation of water on Earth. He proposed that the vast variety of substances in the world must be understood in terms of a single, unitary, simple constituent, which he called apeiron, the indistinct. He even suggested that animals and plants evolve and adapt to changes in the environment, and that man must have evolved from other animals. Thus, gradually was founded the basis of a grammar for understanding the world, which is substantially still our own today. Situated at a crossroads between the emergent Greek civilization and the ancient empires of Mesopotamia and Egypt, nourished by their knowledge but immersed in the liberty and political fluidity typically Greek, Miletus was a place where, for the first time, men decided their own laws collectively in open agoras, where the first parliament in history gathered, and where men first doubted that only the gods could account for the mysteries of the world. This is the immense legacy of Miletus, the cradle of philosophy, natural sciences, and historical studies. It is no exaggeration to say that the entire scientific and philosophical tradition, Mediterranean and then modern, has a crucial root in the speculations of the thinkers of Miletus. This luminous city came to a calamitous end, destroyed by the Persian Empire. But 20 years later, the Greeks repelled the Persian menace, and Miletus was reborn, repopulated, radiating its thought and spirit once more. It was this spirit that moved Leucippus when, in 450, he embarked for Abdera. Little is known about his life. He wrote a book entitled The Great Cosmology. On his arrival in Abdera, he founded a scientific and philosophical school, where he was soon joined by a young disciple, Democritus, whose long shadow was to be cast over the thought of all subsequent times. Together, these two thinkers built the majestic cathedral of ancient atomism. Leucippus was the teacher, Democritus the great pupil, who wrote dozens of works on every field of knowledge, from physics and philosophy to ethics and politics. The most subtle of the ancients, Seneca called him. What then had Leucippus and Democritus discovered? The Milesians had understood that the world can be comprehended using reason. They had become convinced that the variety of natural phenomena must be attributable to something simple. Anaximenes had imagined this substance could compress and rarefy, transforming into the different elements. It was a first germ of physics, rough and elementary, but in the right direction. An idea was needed, a great idea, a grand vision to grasp the hidden order of the world. Leucippus and Democritus came up with this idea. The idea of Democritus's system is extremely simple. The entire universe is made up of a boundless space in which innumerable atoms run. Space is without limits. It has neither an above nor a below, neither a center nor a boundary. The atoms themselves have no qualities at all, apart from their shape. They have no weight, no color, no taste. By convention is sweet, by convention bitter, by convention hot, by convention color, but by verity atoms and void. The atoms are indivisible. They are the elementary grains of reality, which cannot be further subdivided. Everything is made of them. They move freely in space, colliding with one another, hooking onto and pushing and pulling each other. Similar atoms attract each other and join together. This is the weave of the world. This is reality. Everything else is nothing but a byproduct, random and accidental, of this ceaseless movement and combining of atoms. The infinite variety of the substances of which the world is made derives solely from this combining of atoms. When atoms aggregate, the only thing that matters is their shape, their arrangement, and the order in which they combine. Just as by combining the letters of the alphabet in different ways we may obtain comedies or tragedies, so elementary atoms combine to produce the world in its endless variety. The metaphor is Democritus's own. There is no finality, no purpose in this endless dance. We, just like the rest of the natural world, are one of the many products of this dance, the product of an accidental combination. Nature continues to experiment with forms, and we, like the animals, are the products of a random selection over eons of time. Our life is a combination of atoms. Our thoughts are made of thin atoms. Our dreams, the products of atoms. The seas are made of atoms, as are our cities and the stars. It's an immense, boundless, incredibly simple, and incredibly powerful vision. On this foundation, Democritus built a vast system. He wrote on the nature of language, on religion, on the origins of human societies. The opening of his little cosmology is impressive. In this work I treat of all things. But tragically, all of these books have been lost. We know of his thought only through quotations and references from other ancient authors. What emerges is a kind of intense humanism, rationalist and materialist. He combines a keen attention to nature, illuminated by a clarity in which every mythic idea is cleared away, with a deep ethical concern for life, anticipating the best aspects of the 18th century Enlightenment. The ethical ideal of Democritus is a serenity of mind reached through moderation and balance, by trusting in reason. Plato and Aristotle were familiar with his ideas and fought against them. They rejected his naturalistic explanations in favor of trying to understand the world in finalistic terms, believing everything happens for a purpose, a way of thinking that would prove very misleading for understanding nature. Plato never even cites Democritus, a deliberate choice, scholars suspect. In his Phaedo, Plato has Socrates complain that when physicists explained the earth was round, he wanted to know what good it was for the earth to be round. How completely off track the great Plato was here. The greatest physicist of the second half of a much later century, Richard Feynman, wrote at the beginning of his wonderful lessons on physics, "If, in some cataclysm, all scientific knowledge were to be destroyed, and only one sentence passed on to the next generation, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another." Without needing anything from modern physics, Democritus had already arrived at this idea. How did he do it? He had arguments from observation, imagining that the wearing down of a wheel or the drying of clothes was due to the slow flight of particles of wood or water. But he also had arguments of a philosophical kind, arguments whose potency reaches all the way to quantum gravity. Democritus observed that matter could not be a continuous whole, because there is something contradictory in the proposition. Imagine, he says, that matter is infinitely divisible. Imagine you break up a piece of matter ad infinitum. What would be left? Could small particles of extended dimension remain? No, because then it would not be broken up to infinity. So only points without extension would remain. But if you try to put the matter back together from these points, you cannot. 2 points without extension cannot make an extension, nor can 3 or 4. You never regain extension. The only possibility, Democritus concludes, is that any piece of matter is made of a finite number of discrete, indivisible pieces, each with a finite size, the atoms. This subtle argumentation predates Democritus. It comes from Elea, a Greek colony in southern Italy, where Parmenides and his pupil Zeno lived. Zeno had brought subtle arguments to bear in support of fundamentalist rationalism, which refutes the credibility of appearances. Among these were the celebrated Zeno's paradoxes, which seek to show that the notion of motion is absurd. The most famous is the fable of Achilles and the tortoise. The tortoise challenges Achilles to a race with a 10-meter head start. Zeno argues that Achilles will never be able to catch up. Before he can, he must cover the 10 meters, which takes some time. During this time, the tortoise advances a few centimeters. To cover these centimeters, Achilles takes more time, but the tortoise advances further, and so on, ad infinitum. Zeno argues that an infinite number of times is an infinite amount of time. Since we do see Achilles overtake tortoises, what we see must be illusory. Where is the error? One answer is that an infinite number of things does not necessarily make an infinite thing. An infinite number of ever shorter time intervals can add up to a finite time. This is the idea of the continuum. But is this really how the world works? Do arbitrarily short strings or times exist? This is precisely the problem quantum gravity must face. According to tradition, Zeno had met Leucippus and become his teacher. Leucippus was therefore familiar with Zeno's riddles, but he devised a different way of resolving them. Maybe, Leucippus suggests, nothing arbitrarily small exists. There is a lower limit to divisibility. The universe is granular, not continuous. An extension must be formed by a finite number of finite objects. Matter is not continuous. It is made of individual atoms of a finite size. Whether this abstract argument is correct or not, its conclusion, as we know today, contains a great deal of truth. Matter does indeed have an atomic structure. If I divide a drop of water, I get 2 drops of water. I can divide them again, and so on. But I cannot continue to infinity. At a certain point, I have only 1 molecule of water, and I am finished. No drop of water exists smaller than a single molecule. Evidence for this accumulated over centuries, but still, at the beginning of the last century, renowned scientists like Ernst Mach did not believe in atoms. You can't see atoms, they would say. And then, how big would an atom be? Democritus could never measure their size. But someone else could. The definitive proof of the atomic hypothesis had to wait until 1905. It was found by a rebellious 25-year-old working as an employee in the patent office in Bernay. His name, of course, was Albert Einstein. The idea is surprisingly simple. If we observe very small particles, like a speck of dust suspended in still air, we see them tremble and dance. This is called Brownian motion. It is as if the small particle is receiving random blows from all sides. In fact, it is being hit. It trembles because it is hit by individual molecules of air. The subtle point is this. There are an enormous number of molecules. On average, as many hit the granule from the left as from the right. If the molecules were infinitely small and infinitely numerous, the effect would balance perfectly at each instant, and the granule would not move. But the finite size of the molecules means the collisions never balance out exactly. They only balance on average. This causes fluctuations. The smaller the molecules, the better the hits cancel out, and the less the granule moves. It is possible, with a little mathematics, to work back from the amount of movement of the granule to the dimensions of the molecules. Einstein did this. From observations of granules drifting in fluids, he calculated the dimensions of Democritus's atoms, the elementary grains of which matter is made. He provided, after 300 years, the proof of the accuracy of Democritus's insight. Matter is granular. I often think that the loss of the works of Democritus in their entirety is the greatest intellectual tragedy to ensue from the collapse of the old classical civilization. Just imagine what we have lost. The list of his works is heartbreaking. On the planets, on nature, on the nature of man, on the senses, on the mind, on colors, on geometry, on numbers, on music, on rhythm and harmony, on agriculture, on painting, on tactics and fighting in armor. All gone. We have been left with all of Aristotle, by way of which Western thought reconstructed itself, and nothing by Democritus. Perhaps if his works had survived, the intellectual history of our civilization would have been better. But centuries dominated by monotheism did not permit the survival of his naturalism. The closure of the ancient schools of Athens and Alexandria, and the systematic destruction of all texts, not in accordance with Christian ideas at the time of Emperor Theodosius, were vast and brutal. Plato and Aristotle, with their immortal souls and prime movers, could be tolerated. Not Democritus. But one text survived this disaster and has reached us in its entirety. Through it, we know the spirit of that ancient science. It is the splendid poem, De Rerum Natura, the nature of things, by the Latin poet Lucretius. Lucretius adheres to the philosophy of Epicurus, a pupil of Democritus. His vision of the natural world is substantially that of the great philosopher of Abdera. Lucretius decants in verse the thought of Epicurus and the atomism of Democritus, and in this way, a part of this profound philosophy was saved from the intellectual catastrophe of the Dark Ages. He sings of atoms, the sea, the sky, of nature. The beauty of the poem lies in the sense of wonder, which pervades the vast atomistic vision, the sense of the profound unity of things, derived from the knowledge that we are all made of the same substance as the stars and the sea. We are all sprung from heavenly seed, all alike have the same Father, from whom all nourishing Mother Earth receives the showering drops of moisture. There is a sense of luminous calm and serenity, which comes from understanding that there are no capricious gods demanding difficult things of us. There is a deep acceptance of life and a serene acceptance of the inevitability of death, about which there is nothing to fear. For Lucretius, religion is ignorance. Reason is the torch that brings light. This text, forgotten for centuries, was rediscovered in January 1417 by the humanist Poggio Bracciolini in the library of a German monastery. Its rediscovery had a profound effect on the Italian and European Renaissance. Its echo resounds in the pages of authors from Galileo and Kepler to Bacon and Machiavelli. In Shakespeare, a century after Poggio, atoms make a delightful appearance in Mercutio's speech about Queen Mab, drawn with a little team of atomies. The direct influence of Lucretius extended to Newton, Dalton, Spinoza, Darwin, and all the way up to Einstein. The very idea of Einstein's that the existence of atoms is revealed by Brownian motion may be traced back to Lucretius. Here is the passage where Lucretius provides a living proof of atoms. Observe what happens when sunbeams are admitted into a building. You will see a multitude of tiny particles mingling in a multitude of ways, as though contending in everlasting conflict. From this you may picture what it is for the atoms to be perpetually tossed about in the illimitable void. Their dancing is an actual indication of underlying movements of matter that are hidden from our sight. Einstein resuscitated this living proof and made it solid by translating it into mathematical terms, calculating the size of the atoms. An entire vision of the world, swept away by medieval Christian fundamentalism, was re-emerging. It was not just rationalism and materialism. It was a complex structure of thinking about reality, a new mode of thought. The medieval cosmos of Dante was based on a hierarchical organization of the universe, reflecting the hierarchical organization of society. There is none of this in the world of Democritus, as sung by Lucretius. There is a deep love of nature, a serene immersion within it, a recognition that we are profoundly part of it. There is a feeling of deep universalism, echoing Democritus's splendid words. To a wise man, the whole earth is open, because the true country of a virtuous soul is the entire universe. And there is the ambition to think about the world in simple terms, to investigate and understand its secrets. The first person to make the parts of this mosaic cohere and to reprise the Democritean vision, immensely reinforced, placing it at the center of modern thought. Will be an Englishman, the greatest scientist of all time and the first protagonist of our next quiet exploration. If in our last reflection I appeared to be saying that Plato and Aristotle have only done harm to the development of science, I would like to correct this impression. Aristotle's studies of nature, of botany and zoology, for example, are extraordinary scientific works grounded upon meticulous observations. His conceptual clarity and openness of mind made him an authority for centuries. The first systematic physics we know of is Aristotle's. He distinguished between the heavens and the earth. In the heavens, everything is made of a crystalline substance which moves in eternal circles around the spherical earth. On earth, motion is either forced or natural. Forced motion is caused by a thrust. Natural motion is vertical, upwards, or downwards. Each substance has a natural place. Earth at the bottom, water above it, air higher still, and fire highest of all. A stone falls because it wants to return to its natural level. Air bubbles and water move upwards, seeking their natural place. Do not smile at this theory, for it is very sound physics. It's a good and correct description of the motion of bodies immersed in a fluid and subject to gravity and friction, the real things we meet in our everyday experience. It's not wrong physics, it's an approximation, but Newton's physics too is an approximation of general relativity. The physics of Aristotle is rough, but coherent and rational. Perhaps even more important for the future was Plato. It is he who understood the value of the intuition of Pythagoras, that the key to moving forwards was mathematics. Pythagoras, a disciple of the elderly Anaximander, had discovered the theoretical utility of mathematics. Number governs forms and ideas. Plato divested this of its mystical baggage and absorbed its useful message. Mathematics is the language best adapted to describe the world. Driven by this conviction, Plato posed the momentous question that would, after a long detour, give birth to modern science. He asked his disciples to find the mathematical laws followed by the celestial bodies. Venus, Mars, and Jupiter move a little at random among the other stars. Is it possible to find a mathematics which is able to describe and predict their movements? The exercise began with Eudoxus in Plato's school and was pursued for centuries by astronomers like Aristarchus and Hipparchus, bringing ancient astronomy to an extremely high level. We know of these triumphs thanks to a single surviving book, The Almagest of Ptolemy. Ptolemy, an astronomer in Alexandria in the 1st century of our era, presents a mathematical system capable of predicting the seemingly random movements of the planets with almost complete precision. The book is proof that Pythagoras' intuition was correct. Mathematics allows the world to be described and the future to be predicted. After the collapse of ancient science, no one in the Mediterranean was capable of understanding Ptolemy. In India, where Greek learning had arrived, the books were studied and understood. From India, this knowledge returned to the West via learned Persian and Arab scientists. But astronomy did not take a significant step forward for over 1,000 years. Then, at the same time as Poggio Bracciolini discovered Lucretius, the heady atmosphere of Italian humanism intoxicated a young Pole studying in Italy, Nicolaus Copernicus. He studied Ptolemy's Almagest and fell in love with it. He decided to spend his life doing astronomy. More than 1,000 years after Ptolemy, Copernicus made the leap forward. Instead of describing heavenly bodies turning around the Earth, he wrote a revised version of the Almagest, in which the Sun is at the center and the Earth, with the other planets, runs around it. In reality, his calculations did not work much better than Ptolemy's, but the idea was sound. In the succeeding generation, Johannes Kepler showed that the Copernican system could really be made to function better. Painstakingly analyzing new, precise observations, Kepler showed that a few new mathematical laws could describe with exactitude the movements of the planets around the Sun, with a degree of accuracy greater than any obtained in antiquity. We are now in 1600. While Kepler in the cold north calculates movements in the sky, in Italy, it is with Galileo Galilei that the new science begins to take off. Exuberant, Italian, polemical, exceptionally intelligent, Galileo gets a new invention from Holland, the telescope, and points it towards the sky. He sees things people wouldn't believe. Rings around Saturn, mountains on the moon, phases of Venus, moons orbiting Jupiter. Each of these phenomena renders Copernicus's ideas more plausible. But Galileo's grand idea is the logical deduction from this cosmic revolution. Convinced that the Earth is a planet like all others, he reasons that if movements in the heavens follow precise mathematical laws, and if the Earth is part of the heavens, then there must also exist precise mathematical laws governing the movements of objects on Earth. Confident in the Pythagorean Platonic vision, Galileo decides to study how objects fall. He lets objects fall and seeks to measure precisely their falling speed. The result is momentous. Objects do not fall at a constant speed. Their speed, instead, gradually increases. What is constant is not the speed, but the acceleration, the rate at which speed increases. And magically, this acceleration turns out to be the same for all objects. Its value is approximately 9.8 meters per second. For every second an object falls, its speed increases by 9.8 meters per second. This is the first mathematical law discovered for earthly bodies. But the greatest result is still to come, and it will be Isaac Newton who will attain it. Newton studies in depth the results of Galileo and Kepler and, by combining them, finds the hidden diamond. We can follow his reasoning in terms of the little moon, as he himself tells it. Imagine, writes Newton, that the Earth had many moons. Imagine a little moon which orbits the Earth at a minimal distance, just above the mountain peaks. At what speed would this little moon travel? One of Kepler's laws relates the radius of an orbit with its period. We know the radius of the real moon's orbit and its period, 1 month. We know the radius of the little moon's orbit, the radius of the Earth. With a simple proportion, we can compute the period of the little moon's orbit. The result is 1 hour and a half. An object which orbits does not go straight. It continually changes direction, and a change of direction is an acceleration. The little moon accelerates towards the center of the Earth. This acceleration is easy to compute. Newton makes the simple calculation, and the result is 9.8 meters per second, the same acceleration as in Galileo's experiments for falling bodies on Earth. Coincidence? It can't be, reasons Newton. If the effect is the same, the cause must be the same. And so, the force which causes the little moon to turn around its orbit must be the same as that which causes objects to fall to the ground on Earth. We call the force causing objects to fall gravity. Newton understands that it is this same gravity that makes the little moon turn around the Earth. Without this gravity, it would run away in a straight line. But then, the real moon must orbit the Earth because of gravity. And the moons of Jupiter are attracted by Jupiter, and the planets which turn around the sun are attracted by the sun. An immense vision takes shape. Suddenly there is no longer a separation between the heavens and Earth. There is no natural level for things. The universe is a large space where bodies attract one another by means of a universal force, gravity. The world of Newtonian mechanics is simple and is summarized by this vision, a world of Democritus reborn, a vast, undifferentiated space, always equal to itself, where particles run forever and act upon each other. But now the vision is immensely more powerful than in Democritus, because it is combined with mathematics, the legacy of Pythagoras. The world of Newton is the world of Democritus, rendered mathematical. The power of this new framework proves to be beyond all expectation. The entire technology of the modern world rests largely upon Newton's formulae. It is still thanks to theories based on his equations that today we build bridges, trains, skyscrapers, and send spaceships to Mars. The modern world would not have been born without passing by way of Newton's little moon. It seemed the final key to understanding reality had been discovered. But is that really all? Newton knew his equations did not describe all the forces that exist. The first problem he left open was to understand the other forces that determine what happens around us. This had to wait until the 19th century, and it led to 2 surprises. The first is that almost all phenomena we see are governed by a single force other than gravity, electromagnetism. It holds together atoms in molecules and electrons in atoms. It makes chemistry and living matter work. It operates in the neurons of our brain and governs our thinking. It creates the friction that stops a sliding object. It turns electric motors. The second and biggest surprise, crucial to our story, is that understanding this force requires an important modification to the world of Newton: the introduction of the notion of a field. The understanding of how electromagnetic force works was made by two Britons, science's oddest couple, Michael Faraday and James Clerk Maxwell. Faraday was an impoverished Londoner without formal education who worked in a bookbindery and then in a laboratory, where he grew into the most brilliant experimenter of 19th century physics. Without knowing mathematics, he wrote one of the best books of physics ever written, virtually devoid of equations. He saw physics with his mind's eye. Maxwell was a rich Scottish aristocrat and one of the greatest mathematicians of the century. Despite their differences, they succeeded in understanding each other and, together, they opened the way to modern physics. At the beginning of the 19th century, little was known about electricity and magnetism, beyond a few amusing sideshow tricks. Faraday, working in his London laboratory full of bobbins, needles, and iron cages, slowly, guided by his hands, was led to an intuition that would become the basis of modern physics. He saw something new. His intuition was this: we must not think of forces acting directly between distant objects, as Newton presumed. We must instead think that there exists an entity diffused throughout space, which is modified by electric and magnetic bodies, and which, in turn, acts upon them. This entity is today called the field. Faraday saw it as formed by bundles of very thin lines, filling space like an invisible, gigantic cobweb. He called these lines of force because they carry the force from one body to another. An object with an electric charge distorts these lines around itself, and these fields produce a force on any other charged object. If you take two magnets in your hands and play with them, feeling the force with which they attract and repel, it is not difficult to experience the same intuition, to feel the field interposed between them. This is a radically different idea from the Newtonian notion of a force acting between distant bodies. But it would have appealed to Newton. Newton himself was perplexed by this attraction at a distance. How does the Earth attract the Moon without anything between them? He had written in a letter, "It is inconceivable that inanimate brute matter should, without the intervention of something else which is not material, operate upon and affect other matter, without mutual contact. That gravity should be innate, inherent, and essential to matter is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it." Newton is deeming his own masterwork to be absurd. He understood that behind the action at a distance there must be something else, but he had no idea what, and left the question to his readers. It was Faraday, the reader, to whom Newton had bequeathed the question, who found the key. Introducing the field, Faraday departed radically from Newton's ontology. The world is no longer just particles moving in space. A new actor, the field, appears on the scene. Maxwell quickly realized that gold had been struck with this idea. He translated Faraday's insight, which Faraday explained only in words, into a page of equations, now known as Maxwell's equations. They describe the behavior of the electric and magnetic fields, the mathematical version of the Faraday lines. Today, these equations are used daily to describe all electric and magnetic phenomena, from electric engines to computers. Almost everything we witness, with the exception of gravity, is well described by Maxwell's equations. But there is more. There is perhaps the most beautiful success of science. Maxwell's equations tell us what light is. Maxwell realized his equations predict that Faraday's lines can tremble and undulate, like the waves of the sea. He computed the speed at which these undulations move, and the result turned out to be the same as for light. Maxwell understood, because light is nothing other than this rapid trembling of Faraday's lines. Not only had they figured out how electricity and magnetism work, but as a collateral effect, they had figured out what light is, We see the world in color. What is color? Simply the frequency of the electromagnetic wave that is light. If the wave vibrates more rapidly, the light is bluer. If it vibrates more slowly, it is redder. Light is thus nothing more than a rapid vibration of the spiderweb of Faraday's lines. It isn't true that we do not see these lines. We only see vibrating Faraday lines. To see is to perceive light, and light is the movement of Faraday lines. The discovery is extraordinary, but there is even more. Maxwell recognized that his equations predicted that Faraday's lines could also vibrate at much lower frequencies. Therefore, there must be other waves which nobody had yet seen. A few years later, these waves were revealed by the German physicist Heinrich Hertz, and a few years after that, Guglielmo Marconi built the first radio. All modern communications technology, radio, television, telephones, computers, satellites, Wi-Fi, the Internet, is an application of Maxwell's prediction. The contemporary world emerges from the intuitions of a poor London bookbinder who saw some lines in his mind's eye, and the work of a good mathematician who translated this vision into equations, understanding that the waves of these lines can carry news from one side of the planet to the other. The world has changed. It is no longer made up of particles in space, but of particles in fields in space. It seems a minor change, but a few decades later, a young Jewish man, a citizen of the world, would draw from it consequences that would go far beyond Faraday's already fervid imagination, and which would shake Newton's world even further to its core. 20th century physics has radically modified the Newtonian image of the world. The new steps are the basis of a great deal of today's technology. This deepening of our understanding is based on two theories: general relativity and quantum mechanics. Both demand a daring reevaluation of our conventional ideas: space and time in relativity, matter and energy in quantum theory. It's here that the magic of 20th century physics begins. Studying and trying to understand them in depth is a bewitching adventure. These two theories are the ground from which we are trying to move forwards. The father of Albert Einstein built power stations in Italy. When Albert was a young boy, the Maxwell equations were only a few decades old, but the turbines and transformers his father constructed were already based on them. Albert was a rebel. He found the German school system too rigid and militaristic and abandoned his studies. He joined his parents in Italy and spent his time loafing. Later, he went to study in Switzerland, initially failing to get into the Zurich Polytechnic. After his university years, he could not find a research position and found employment in the patent office of Bernay. It gave him time to think. At the age of 25, he sent to the Annalen der Physik 3 articles. Each was worthy of a Nobel Prize. The first, as we have seen, proved that atoms exist. The second is the one for which he is most famous, the article in which he introduces the theory of relativity. In fact, there are two theories of relativity. The envelope sent by the 25-year-old Einstein contained the first, the theory known today as special relativity. It is a subtle and conceptually difficult theory. Do not become demoralized if the next few moments sound a bit abstruse. The theory shows that the Newtonian vision of the world must be radically modified in a way that goes completely against common sense. The theories of Newton and Maxwell appear to contradict each other in a subtle way. Maxwell's equations determine a velocity, the velocity of light. But Newton's mechanics is not compatible with the existence of a fundamental velocity. In Newton's physics, velocity is relative. The only velocity that exists is the velocity of an object with respect to another object. But if this is so, then the speed of light determined by Maxwell's equations is velocity. With respect to what? Einstein asked himself whether there was a way of rendering Newton's core discoveries and Maxwell's theory consistent. In doing so, he arrived at a stupefying discovery. Think of all the past, present, and future events with respect to the moment in which you are listening. Imagine them distributed in a simple progression. Well, Einstein's discovery is that this picture is incorrect. Between the past and the future of any event, there exists an intermediate zone, an expanded present, a zone that is neither past nor future. The duration of this intermediate zone, which is neither in your past nor in your future, is very small and depends on where an event takes place relative to you. At a distance of a few meters from you, the duration is no more than a few nanoseconds. On the other side of the ocean, it is 1,000th of a second. But on the Moon, the duration of this expanded present is a few seconds, and on Mars it is 1/4 of an hour. This means we can say that, on Mars, there are events that in this precise moment have already happened. Imagine them distributed in a simple progression. Well, Einstein's discovery is that this picture is incorrect. Between the past and the future of any event, there exists an intermediate zone, an expanded present, a zone that is neither past nor future. The duration of this intermediate zone, which is neither in your past nor in your future, is very small and depends on where an event takes place relative to you. At a distance of a few meters from you, the duration is no more than a few nanoseconds. On the other side of the ocean, it is 1,000th of a second. But on the Moon, the duration of this expanded present is a few seconds, and on Mars it is 1/4 of an hour. This means we can say that, on Mars, there are events that in this precise moment have already happened, events that are yet to happen, but also 1/4 of an hour, during which things occur that are neither in our past nor in our future. They are elsewhere. We had never before been aware of this, elsewhere, because next to us, it is too brief. But it exists. This is why it is impossible to hold a smooth conversation between here and Mars. This 1/4 of an hour is inevitable. It is woven into the texture of space and time. It implies that it makes no sense to say of an event on Mars that it is taking place just now, because just now does not exist. Einstein understood that absolute simultaneity does not exist. There is no collection of events in the universe which exist now. The set of all events has a more complex structure. In the Andromeda galaxy, the duration of this expanded present is 2 million years. Everything that happens during these 2 million years is neither past nor future with respect to ourselves. The discovery of this structure has concrete consequences. As space and time fuse into a single concept of spacetime, so the electric and magnetic fields fuse into a single entity, the electromagnetic field. There is another implication. The concepts of energy and mass become combined. Before 1905, two principles appeared certain: conservation of mass and conservation of energy. But Einstein realized that energy and mass are two facets of the same entity. One may be transformed into the other. What is conserved is the sum of mass and energy. A rapid calculation teaches Einstein how much energy is obtained by transforming 1 gram of mass. The result is the celebrated formula E equals mc squared. Since the speed of light c is a very large number, the energy obtained is enormous, enough to illuminate a city for months, or to destroy one in a second. The theoretical speculations of the young Einstein had transported humanity into a new era. Today, the structure of spacetime proposed by Einstein is well understood and repeatedly tested. Our intuitive idea of the present is an effect of our blindness, our inability to recognize small temporal intervals. It is an illegitimate extrapolation from our parochial experience. The present is like the flatness of the earth, an illusion. The resulting knitted structure that space and time form together is what physicists call spacetime. But despite the outcry provoked by this step, we are not yet at his masterpiece. Einstein's triumph is the second theory of relativity, the theory of general relativity, published 10 years later. This is the most beautiful theory produced by physics, and the first of the pillars of quantum gravity. After publishing special relativity, Einstein becomes a renowned physicist, but something troubles him. Special relativity does not square with what was known about gravity. He realizes this while writing a review of his theory, and wonders whether the venerable theory of Newton should not be reconsidered. Newton had imagined a force of gravity, but how this force managed to draw distant things together was not understood. Faraday had found the solution for electric and magnetic forces, the field. It's clear, at this stage, to any reasonable person, that the force of gravity must have its Faraday lines as well. There must be a gravitational field. That is to say, it was clear only to Albert Einstein. He immersed himself in the problem. It would take 10 years of manic studies, attempts, mistakes, confusion, brilliant ideas, wrong ideas. Finally, in 1915, he committed to print an article containing the complete solution, which he named The General Theory of Relativity, his masterpiece. The reason for its beauty is not hard to see. Instead of simply inventing the mathematical form of the gravitational field, Einstein fished out the other unresolved question in Newton's theory. What is space? For 2 millennia, the Democritian idea of space as a peculiar entity distinct from things had never been seen as reasonable. For Aristotle, as for Descartes, extension is a property of things. It does not exist without something being extended. What is this empty space within which particles move? Is it something or is it nothing? Newton, who resuscitated the idea of space, had tried to patch things up by arguing that space was God's sensorium, but no one has ever understood what he meant by this. Einstein found Newton's explanation unconvincing. Thus, Einstein addresses 2 problems. First, how to describe the gravitational field. Second, what is Newton's space? And it's here that Einstein's extraordinary stroke of genius occurs, one of the greatest flights in the history of human thinking. What if the gravitational field turned out actually to be Newton's mysterious space? What if Newton's space was nothing more than the gravitational field? This extremely simple, beautiful, brilliant idea is the theory of general relativity. The world is not made up of space plus particles plus fields. The world is made up of particles plus fields and nothing else. There is no need to add space as an extra ingredient. Newton's space is the gravitational field. It is a momentous simplification of the world. Space is no longer different from matter. It is one of the material components of the world. It is a real entity which undulates, fluctuates, bends, and contorts. We are not contained within an invisible, rigid scaffolding. We are immersed in a gigantic, flexible mollusk. The sun bends space around itself, and the earth does not circle around it, drawn by a mysterious distant force, but runs straight in a space that inclines. It's like a bead which rolls in a funnel. Planets circle around the sun, and things fall, because space around them is curved. More precisely, what curves is not space, but space-time. Einstein's only problem was to find the equations to make it concrete. And here he was, lucky. The problem had already been solved by the mathematicians. The greatest mathematician of the 19th century, Carl Friedrich Gauss, had written maths to describe curved surfaces. Then he had asked a talented student, Bernhard Riemann, to generalize this to curved spaces in 3 or more dimensions. Riemann produced a ponderous doctoral thesis of the kind that seems completely useless. His result was that the properties of a curved space are described by a particular mathematical object, now called Riemann curvature, R. With a great deal of effort, Einstein learned Riemann's maths and wrote an equation where R is proportional to the energy of matter. In words, space-time curves more where there is matter. That is it. A vision becomes an equation. But within this equation there is a teeming universe. And here the magical richness of the theory opens up into a phantasmagorical succession of predictions that resemble the delirious ravings of a madman, but which have all turned out to be true. To begin with, Einstein recalculated the effect of the sun's mass on the curvature of space and its effect on the movements of the planets. He found the movements as predicted by Newton, but not exactly. In the vicinity of the sun, the effect is stronger. He computed the movement of Mercury and found a small difference from Newton's prediction. The verdict was unequivocal. Mercury follows the trajectory predicted by Einstein. His equation also describes how space curves very close to a star. Due to this curvature, light deviates. In 1919, the measurement was achieved, and the deviation was exactly in accordance with the prediction. But it is not only space that curves, time does too. Einstein predicted that time on Earth passes more quickly at higher altitude and more slowly at lower altitude. This was measured and also proved to be the case. Place a watch on the floor and another on a table. The one on the floor registers less passing of time. The Earth, like all masses, distorts space-time, slowing time down in its vicinity. The predictions go well beyond these minute effects. When a large enough star burns out its fuel, it collapses under its own weight. Matter is squashed down to an enormous degree, and space curves so intensely as to plunge down into an actual hole. A black hole. When I was a university student, black holes were regarded as a scarcely credible implication of an esoteric theory. Today, they are observed in their hundreds. The theory also predicts that space ripples like the surface of the sea. The effects of these gravitational waves can be observed in binary stars. These waves were directly observed by an antenna on Earth in late 2015, leaving the world speechless. And further still, the theory predicts that the universe is expanding and emerged from a cosmic explosion 14 billion years ago. This rich and complex range of phenomena follows from understanding that space is not a dull, fixed container, but possesses its own dynamic. Democritus himself would have smiled with pleasure. It is true that he termed space non-being, but what he meant by being was matter, and he wrote that his non-being, the void, nevertheless, has a certain physics and a substantiality of its own. How right he was. All of this sounds like a tale told by an idiot, full of sound and fury, signifying nothing. And yet, instead, it is a glance towards reality, a reality which seems to be made of the same stuff our dreams are made of, but which is nevertheless more real than our clouded daily dreaming. And all this is the result only of an elementary intuition that space-time and the gravitational field are one and the same thing, and a simple equation. 2 years after the publication of his equation, Einstein decides to use it to describe the space of the entire universe. And here he has another of his amazing ideas. For thousands of years, men had asked whether the universe was infinite or had a limit. Both hypotheses entail thorny problems. But Einstein finds a third way. The universe can be finite and at the same time have no boundary. How? Just as the surface of the Earth is not infinite but does not have a boundary, this can happen if something is curved. And in general relativity, three-dimensional space can also be curved. Consequently, our universe can be finite but borderless. On the surface of the Earth, if I were to keep walking in a straight line, I would eventually get back to where I started. Our universe could be made in the same way. A three-dimensional space of this kind is called a three-sphere. However incredible it might seem, the same idea had already been conceived by another genius from an entirely different cultural universe, Dante Alighieri. In the Paradiso, Dante offers a grandiose vision of the medieval world with the spherical Earth at its center, surrounded by celestial spheres. Accompanied by Beatrice, he ascends these spheres up to the outermost one. But then, he looks even higher, and what does he see? He sees a point of light, surrounded by immense spheres of angels, another immense ball, which, in his words, surrounds and is at the same time surrounded by the sphere of our universe. It is an exact description of a three-sphere. How is it possible that Dante had an idea that sounds so modern? I think it was possible due to the profound intelligence of Italy's finest poet. But it is also due to the fact that he was writing well before Newton convinced everyone that the space of the cosmos was the flat one of Euclidean geometry. Dante was free of the restraints upon our intuition. When Einstein tries to insert the idea of the three-sphere into his equations, he encounters a problem. He is convinced the universe is fixed and immutable, but his equations tell him this is not possible. Everything attracts, therefore the only way for a finite universe not to collapse is for it to be expanding. But Einstein does not believe his own equations. He even makes a silly physics mistake just to avoid accepting what his theory predicts. He modifies his equations, trying to avoid the implication. It is a further mistake. For all his bravery, Einstein the genius lacks the courage to believe his own equations. A few years later, he is forced to give up. His theory is right, not his reservations about it. Astronomers realize that all galaxies are indeed moving away from us. The universe is expanding. 14 billion years ago, the universe was concentrated almost to a single, furiously hot point. From there it expanded in a colossal cosmic explosion. This is the Big Bang. The definitive proof arrives in 1964, when two American radio astronomers, Arno Penzias and Robert Wilson, discover by accident a radiation diffused throughout the universe, which is precisely what remains of the original immense heat. Once again, the theory turns out to have been correct. Ever since we discovered that the Earth is round and turns like a mad spinning top, we have understood that reality is not what it seems. But the leap made by Einstein is unparalleled. Spacetime is a field. The world is made only of fields and particles. Space and time are not something else, but just a field among the others. The two pillars of 20th century physics, general relativity and quantum mechanics, could not be more different from each other. General relativity is a compact jewel, conceived by a single mind. Quantum mechanics, on the other hand, emerges from experiments over a quarter of a century, to which many have contributed. It achieves unequaled experimental success, but remains shrouded in obscurity. This next exploration will illuminate the strange physics of this theory and the three aspects of reality it has unveiled: granularity, indeterminism, and relationality. It's said that quantum mechanics was born precisely in 1900. The German physicist Max Planck, trying to compute the amount of electromagnetic waves in a hot box, used a trick. He assumed the energy of the electric field is distributed in quanta, small packets of energy. The size of the packets, he assumed, depends on the frequency of the waves. For waves of frequency nu, every quantum has energy, E equals h nu. This is the first formula of quantum mechanics. H is a new constant, the Planck constant. The idea that energy could be made of finite packets was at odds with everything known at the time. For Planck, it was just a strange trick that happened to work. 5 years later, it is Albert Einstein, him again, who comes to understand that Planck's packets of energy are in fact real. This is the subject of the third of his 3 articles of 1905. In it, Einstein argues that light is truly made up of small grains, particles of light. He considers the photoelectric effect. There are substances that generate a weak electric current when struck by light. It seems reasonable that if the light is dim, the phenomenon wouldn't happen, and it would if the light is bright. But it isn't like this. The phenomenon happens only if the frequency of light is high, not if it is low. It depends on the color of light, not its intensity. Einstein uses Planck's idea. Imagine light arrives in grains of energy. An electron will be swept out of its atom if the individual grain hitting it has enough energy. What matters is the energy of each grain, not the number of grains. If the energy of each grain is determined by frequency, the phenomenon will occur only if the frequency is high enough. It is like when it hails. What determines whether your car will be dented is the size of the individual hailstones, not the total quantity of hail. For this simple reasoning, Einstein was awarded the Nobel Prize. Today we call these packets of energy, photons, 2kL. They are the grains of light. If Planck is the biological father of the theory, Einstein is the parent who gave birth to and nurtured it. But the theory then went its own way. During the first 2 decades of the 20th century, it is the Dane Niels Bohr who guides its development. He studies the structure of atoms which were beginning to be explored. Experiments had shown that an atom is like a small solar system, with a heavy central nucleus and light electrons revolving around it. This picture, however, did not account for a simple fact. Matter is colored. Salt is white, pepper is black, chili is red. Why? Studying the light emitted by atoms, it is apparent that substances have specific colors, or spectra. Spectra are collections of fine lines of different hues. But in Newton's mechanics, an electron can revolve at any speed and emit light at any frequency. Why are atomic spectra not a continuum of colors, but just a few separate lines? Bohr finds a tentative solution. He realizes everything could be explained if the energy of electrons in atoms could only assume certain, quantized values. it begins to become clear that granularity is widespread in nature. Bohr makes the hypothesis that electrons can exist only at certain, special distances from the nucleus. On certain particular orbits, electrons can leap between these permitted orbits. These are the famous quantum leaps. The frequency at which the electron moves determines the frequency of the emitted light, and since only certain orbits are allowed, only certain frequencies are emitted. The experimental success of this simple model is astonishing. But why are there always only just certain orbits, and what does it mean to say that electrons leap? In Bohr's Institute in Copenhagen, the most brilliant young minds of the century gather to try to construct a coherent theory. A young German finds the key, Werner Heisenberg. The intuition comes to him one night in the park behind the institute. It is really dark there. Suddenly, he sees a figure pass by. He sees him appear beneath a lamp, then disappear into the dark before reappearing beneath another. And so on. Heisenberg thinks that, evidently, the man does not actually vanish and reappear. He is a substantial object. But what about electrons? A light flashes on in his mind. What if, effectively, electrons could vanish and reappear? What if these were the mysterious quantum leaps? What if an electron could be something that manifests itself only when it interacts, and that between one interaction and another it had no precise position? Heisenberg returns home and plunges into calculations. He emerges with a disconcerting theory, a fundamental description of the movement of particles, in which they are described not by their position at every moment, but only by their position at particular instants, the instants in which they interact. This is the second cornerstone of quantum mechanics, its hardest key, the relational aspect of things. An electron is a combination of leaps from one interaction to another. When nothing disturbs it, an electron does not exist in any place. In the end, it is another 25-year-old who picks up the work and constructs its entire formal scaffolding. The Englishman Paul Adrien Maurice Dirac. Silent, reserved, incapable of expressing emotions, he seemed virtually autistic. Yet in his hands, quantum mechanics is transformed from a jumble of intuitions into a perfect architecture, airy, simple, and extremely beautiful. For him, the world is not made of things. It's constituted of an abstract mathematical structure which shows us how things appear. Dirac's quantum mechanics is the theory used today by any engineer, chemist, or molecular biologist. In it, every object is defined by an abstract space and has no property in itself, apart from those that are unchanging, like mass. Its position, velocity, and so on acquire reality only when it interacts with another object. The relational aspect becomes universal. When a variable appears, it does not assume just any value. Dirac provides the recipe to compute the set of values it can take. We call this set the spectrum of that variable. The theory also gives the probability that one value or another will manifest. This is a radical change from Newton's theory, where the future can be predicted with certainty. Quantum mechanics brings probability to the heart of things. This indeterminacy is the third cornerstone. The apparent determinism of our world is due only to the fact that microscopic randomness cancels out on average. Shortly after completing the general formulation of the theory, Dirac realized it could be applied to fields like the electromagnetic one. He discovered a profound simplification, the convergence between the notion of particles and the notion of fields. The cloud of probability that accompanies an electron resembles a field. The fields of Faraday and Maxwell, in turn, are made of grains, photons. The notions merge. The electromagnetic waves are vibrations of Faraday's lines, but also, at a small scale, swarms of photons. The electrons and all other particles are equally quanta of a field. The general form of the theory is called quantum field theory. During the 20th century, the list of fundamental fields was updated, and today we have the standard model of elementary particles, which describes almost everything we see, with the exception of gravity. It has been a triumph. So let's attempt some conclusions about what quantum mechanics tells us about the world. It has revealed three aspects of nature: granularity, indeterminacy, and the relational structure of the world. First, granularity. The information in the state of a system is finite. Planck's constant, h, measures the elementary scale of this granularity. Second, indeterminacy. The world is a sequence of granular quantum events. The future is genuinely unpredictable. Chance operates at the atomic level. Third, and most profound, relationality. The theory does not describe things as they are. It describes how they occur and interact. The world of existent things is reduced to a realm of possible interactions. Reality is reduced to relation. In a certain sense, this is a radical extension of relativity. All variable aspects of an object exist only in relation to other objects. It isn't things that enter into relations, but rather relations that ground the notion of thing. The world of quantum mechanics is not a world of objects. It is a world of events. A stone is a vibration of quanta that maintains its structure for a while, just as a marine wave maintains its identity for a while. Quantum mechanics teaches us to think of the world in terms of processes. But do we really understand? It seemed absurd to Einstein. On the one hand, he proposed Heisenberg and Dirac for the Nobel Prize. On the other, he grumbled that none of it made much sense. He devised mental experiments to show that the new ideas were contradictory. Niels Bohr patiently explained them. The dialogue continued for years. In the end, Einstein accepted that the theory was coherent, but he remained convinced that things could not be as strange as it proposed. That, behind it, there must be a more reasonable explanation. A century has passed, and we are at the same point. Richard Feynman wrote, "I think I can state that nobody really understands quantum mechanics. The interpretation I have presented here is the relational interpretation, right? It seems the least unreasonable to me. But there is no consensus. Perhaps the obscurity is not the fault of the theory, but the limited capacity of our imagination. We are like moles used to living underground to whom someone is trying to describe the Himalayas. Or, like the men in Plato's cave, when Bohr died, someone took a photograph of the blackboard in his study. There's a drawing on it. It represents the box of light of Einstein's thought experiment. To the very last, the desire to debate, to understand more. To the very last, doubt. This permanent doubt, the deep source of science. If you have followed me this far, you now have all the elements to understand the current image of the world suggested by fundamental physics. There is a curved space-time born 14 billion years ago and still expanding. This space is a real object, a physical field described by Einstein's equations. Matter is made up of quantum fields that manifest as particles or waves. With this image, we can describe almost everything we see. Almost. Something is missing. Turning the page, you pass from what we credibly know to what we don't yet know but are trying to glimpse. You are leaving the security of our small spacecraft of near certainties and stepping into the unknown. There is a paradox at the heart of our understanding. General relativity and quantum mechanics, the two jewels of the 20th century, have been prolific in gifts. But between them, there is something that grates. They cannot both be true, at least not in their present forms, because they contradict each other. In the morning, a university student learns the world is a curved space-time where everything is continuous. In the afternoon, the world is a flat one where discrete quanta of energy leap. The paradox is that both theories work remarkably well. Nature continues to say, "You are right," to both. It is clear something eludes us. In most situations, we can neglect one or the other. But there are situations where both curvature and quantum granularity matter, and for these we do not have an established theory. An example is the interior of black holes. Another is what happened during the Big Bang. In more general terms, we do not know how space and time behave at a very small scale. The problem goes deeper. Einstein understood that space and time are manifestations of a physical field, the gravitational field. Bohr, Heisenberg, and Dirac understood that fields are quantum. It follows that space and time must also be quantum entities. What, then, is quantum space? What is quantum time? This is the problem of quantum gravity. A band of theoretical physicists is laboriously seeking to solve it. Their objective is to find a theory, a coherent vision of the world, to resolve the current schizophrenia. It isn't the first time physics has faced such a conflict. Newton discovered universal gravity by combining Galileo's physics of Earth with Kepler's physics of the heavens. Einstein found relativity to resolve the conflict between Newton's mechanics and Maxwell's electromagnetism. Theoretical physicists are happy when they discover a conflict of this type. It is an extraordinary opportunity. The first to realize our conceptual basis must change was a romantic, legendary character, Matvei Bronstein, a young Russian who lived during the Stalin era. He was a younger friend of Lev Landau, the best theoretical physicist of the Soviet Union. Colleagues said Matvei was the more brilliant. Landau had thought that fields became ill-defined due to quanta. Bohr showed he was wrong for the electric field. But Matvei, intrigued, applied the same reasoning to the gravitational field. And here, surprise, Landau was right. The gravitational field at a point is not well defined. Suppose we want to observe a very small region of space. We place a particle there. Heisenberg's uncertainty principle tells us the smaller the region, the greater the velocity at which it escapes. Great velocity means great energy. Einstein's theory tells us energy makes space curve. A lot of energy in a small region curves space so much it collapses into a black hole. But if a particle plummets into a black hole, I can no longer see it. I can't measure arbitrarily small regions of space. Quantum mechanics and general relativity, taken together, imply a limit to the divisibility of space. Below a certain scale, nothing more is accessible. This minimum length is the Planck length, about 10 cubed centimeters. So that is to say, small. It is at this scale that quantum gravity manifests. Matvei Bronstein understood this in the 1930s. There is, however, a problem. Matvei and Lev were sincere communists. When Stalin assumed power, they were critical. These were harsh times. Landau survived. Matvei, the year after having been the first to understand that our ideas on space and time had to change, was arrested by Stalin's police and condemned to death. His execution took place on the same day as his trial, February 18, 1938. He was 30 years old. After his premature death, many eminent physicists tried to solve the puzzle. Darwin dedicated his final years to it. Feynman tried, but without success. Gradually, over decades, ideas were clarified. The scientist who has most contributed is John Wheeler, a legendary figure. A pupil of Bohr, a collaborator with Einstein, a teacher to Feynman. Gifted with a fervid imagination, he invented the term black hole. He imagined quantum space as a cloud of superimposed geometries. On our scale, space is smooth. At the Planck scale, it shatters and foams. In 1966, a young colleague, Bryce DeWitt, provided the key. Wheeler asked him to meet at an airport where he had a layover. Bryce arrived and showed him an equation for a wave function of space. From this conversation, a type of equation of orbitals for general relativity was born, the Wheeler-DeWitt equation. It should determine the probability of one or another curved space. The idea was very good, but the equation was riddled with problems. Mathematically, it was ill-defined. And it was difficult to interpret. It no longer contained the time variable. What does a physical theory without a temporal variable signify? The fog began to dissipate towards the end of the 1980s. Surprisingly, some solutions of the Wheeler-DeWitt equation appeared. During these years, I found myself visiting the Indian physicist Abhay Ashtekar and the American physicist Lee Smolin. Ashtekar had rewritten the equation in a simpler form, and Smolin, with Ted Jacobson, had found some of these new strange solutions. The solutions had a curious peculiarity. They depended on closed lines in space, or loops, dai. What did this mean? The first works of what would later become known as loop quantum gravity emerged from these discussions. Remember Faraday's lines, which carry the electric force. The closed lines that appear in these solutions are Faraday lines of the gravitational field. But there are two new ingredients. The first is that we are dealing with quantum theory, so everything is discrete. The infinitely fine spiderweb of Faraday's lines becomes a real spiderweb with a finite number of threads. The second new aspect, the crucial one, is that we are speaking of gravity. Faraday's lines of the quantum gravitational field are the threads of which space itself is woven. It soon became clear that the key to understanding the physics of these solutions lies in the points where these lines intersect. These are called nodes, and the lines between nodes are called links. A set of intersecting lines forms a graph. A calculation demonstrates that without nodes, physical space has no volume. It is in the nodes that the volume of space resides. The links connect individual volumes. The key technical result that clarifies this picture is the calculation of the spectra of volume and of area. Volume is a property of the gravitational field, but the gravitational field is a physical quantity, subject to the laws of quantum mechanics. It may not assume arbitrary values, but only certain particular ones. The calculation, completed in the mid-1990s, showed that the spectrum of the volume is discrete. Volume can only be made up of discrete packets. The nodes of the graph represent these packets. Every node is a Bona, quantum particle of space, Bona. The links represent the adjacency of these particles. The area, just as in the case of volume, is a physical variable, and its spectrum is also discrete. There is no such thing as an arbitrarily small area. Space appears continuous to us, only because we cannot perceive the extremely small scale of these individual quanta. This brings us back to Achilles and the tortoise. Zeno observed the difficulty in Achilles having to cover an infinite number of distances. Mathematics found an answer in the continuum. But is that what truly happens in nature? The calculation of the quantum spectra of geometric quantities indicates the answer is negative. There is a lower limit to the divisibility of space. Achilles does not need an infinite number of steps, because infinitely small steps do not exist. He reaches the tortoise in a single quantum leap. Was this not precisely the solution proposed by Leucippus and Democritus? The graphs that describe the quantum states of space are characterized by a volume for every node and a half integer, or spin, for every line. A graph with this information is a spin network. A spin network represents a quantum state of space, a granular space where area and volume are discrete. The crucial difference between photons and the nodes of the graph is that photons exist in space, whereas the quanta of gravity constitute space. They have no place to be in, because they are themselves that place. The quanta of gravity are not in space. They are space. Space is created by the interaction of individual quanta of gravity. This is the first step towards understanding quantum gravity. The second concerns time. And to time, our next reflection is devoted. The alert listener will have realized that in the preceding reflection, little attention was given to time, and yet Einstein showed that we must think of them together as a single whole, spacetime. The moment has come to bring time back into the picture. As we abandon the idea of space as an inert container, similarly, we must abandon the idea of time as an inert flow along which reality unfurls. In a certain sense, space no longer exists in fundamental theory. In the same sense, time no longer exists. The fundamental equations no longer contain the time variable. Time emerges, like space, from the quantum gravitational field. This was already partially true for classical general relativity, but when we take quantum mechanics into account, we recognize that time, too, must have aspects of probabilistic indeterminacy, granularity, and relationality. What does it mean to say that time does not exist? First, it does not imply that everything is immobile. On the contrary, it means that change is ubiquitous. Only, elementary processes cannot be ordered along a common succession of instants. Every process dances independently with its neighbors, following its own rhythm. The passing of time is intrinsic to the world, born of the relations between the quantum events that are the world. Let's try to understand. Time appears in most equations of classic physics as the variable t. The equations tell us how things change in time. To discover the law of falling bodies, Galileo needed to measure the height of an object and the time. He needed a clock. There were no accurate clocks. According to legend, he discovered that the oscillations of a pendulum all have the same duration by counting the beats of his own pulse. With excitement, he found the number of beats was the same for each oscillation. But how could he know that his own pulse beats all lasted for the same amount of time? Not many years later, doctors began to measure pulses using a watch, which is a pendulum. So we use the beats to assure ourselves the pendulum is regular, and the pendulum to ascertain the regularity of the beats. Is this not circular? It means that we, in reality, never measure time itself. We always measure physical variables and compare one with another. It is useful to imagine a variable t, the true time, which underpins all those movements, even if we cannot measure it directly. Newton understood this. He asserts explicitly that we can't ever measure the true time t, but if we assume it exists, we can set up an efficient framework to describe nature. Physics without time is physics in which we speak only of the pulse and the chandelier. Without mentioning time, things change only in relation to one another. At a fundamental level, there is no time. Our sense of the common passage of time is only an approximation, valid for our macroscopic scale. Consider a process, the collision of two billiard balls. To deal with this in quantum gravity, it is necessary to include space and time in the process itself. We must describe the two balls and everything around them, the table, the space in which they are immersed during the time that elapses. We are slicing a small, finite portion of Einstein's great mollusk. This process does not occur in time. The passage of time is only the measure of the process itself. Quantum mechanics does not tell us what happens during a process, but the probability that ties together the different initial and final states. In our case, the initial and final states are given by all that happens at the border of our spacetime box. The equations of loop quantum gravity give us the probability associated with a given possible boundary. How is this probability computed? Using Feynman's sum over paths. By considering all possible trajectories that have the same boundary. Since we are including the dynamics of spacetime, this means considering all possible spacetimes which have the same boundary as the box. If quantum space has the structure of a spin network, what structure will spacetime have? A. History of a spin network. Imagine moving the graph. Every node draws a line. Every line draws a surface. A node can open up into two or more nodes. Two or more can combine. A graph which evolves draws an image like a foam of soap bubbles, a spinfoam. To compute the probability of a process, one must sum up over all possible spinfoams within the box that have the same boundary. Spacetime is generated by processes in which spin networks transform into one another. This microscopic swarming of quanta, which generates space and time, underlies the calm appearance of the macroscopic reality surrounding us. So what is the world made of? The backdrop of space has disappeared, time has disappeared, classic particles have disappeared, along with the classic fields. The answer is now simple. The world is made entirely from quantum fields. These fields do not live in space-time. They live one on top of the other, fields on fields. Space and time are our blurred, approximate image of one of these fields, the gravitational field. Covariant quantum fields have become the best description we have of the apeiron, the primal substance hypothesized by Anaximander. The separation between the curved space of general relativity and the discrete quanta of quantum mechanics has dissolved. The conceptual price is relinquishing the idea of space and time as general structures. They are approximations that emerge at a large scale. This rarefied picture of the fundamental structure of the physical world is the vision of reality offered today by quantum gravity. The main reward is that infinity disappears. In 1927, a young Belgian scientist, a Jesuit-educated Catholic priest, studied Einstein's equations and realized they predicted the universe must expand or contract. Instead of rejecting the result, as Einstein did, the priest believed it. He suggested the universe was originally extremely small and compressed and started its expansion in a gigantic explosion. He called this the primordial atom. Today it is the Big Bang. His name was Georges Lemaitre. He met Einstein and tried to dissuade him from his prejudicial view. Einstein resisted, saying, "Correct calculations, abominable physics." Later, Einstein had to recognize Lemaitre was right. When the idea of the Big Bang began to be accepted, Pope Pius XII declared it confirmed Genesis. Lemaitre, with great concern, persuaded the Pope to refrain from this. Lemaitre was convinced it was foolish to mix science and religion. The Bible knows nothing about physics, and physics knows nothing about God. Pius XII was persuaded. To contest both Einstein and the Pope and be right in both cases is surely something of a result. Today, confirmations are overwhelming. But what happened before this initial hot and compressed state? Regressing in time, temperature and density increase. At a certain point, they reach the Planck scale. At that point, the equations of general relativity are no longer valid. We enter the realm of quantum gravity. What do the loops tell us? Consider an electron falling into an atomic nucleus. In classical mechanics, it would be swallowed. But a real electron is a quantum object. It cannot be kept inside too small a region. A quantum repulsion pushes it away. The same applies to the universe. A contracting universe does not collapse to a point. It bounces back and begins to expand, as if emerging from a cosmic explosion. This is the Big Bounce. Our universe could be the result of the collapse of a previous contracting universe, passing through a quantum phase where space and time are dissolved into probabilities. We are beginning to cast the first few cautious glances, for the moment only theoretically, beyond the Big Bang. The appeal of quantum cosmology goes beyond fascinating theoretical explorations. It might provide the opportunity to find out whether the theory is correct. Science works because, after hypotheses and reasoning, we can check. This is its power. Lemaitre defends the expansion of the universe. Einstein does not believe it. One is wrong, the other right. Einstein's fame and authority count for nothing. The observations prove him wrong. The sociology of science has shed light on the complexity of the process, but in the end, it is possible to establish who is right and who is wrong. The importance of experimental proof does not mean that, without new data, we cannot advance. Copernicus had no new data. Neither did Newton or Einstein. They built upon pre-existing theories, finding a way to combine and rethink them. This is how research on quantum gravity operates. Its experimental data are general relativity and quantum mechanics. The most studied alternative to loop quantum gravity is string theory. Most string theorists expected that the new accelerator at CERN, the LHC, would reveal new supersymmetric particles. Loop quantum gravity is well defined without them. The supersymmetric particles were not observed, to the great disappointment of many. This is not definitive proof, but nature has given a small clue in favor of the loops. There have been three major experimental results in recent years: the Higgs boson, the Planck satellite measurements confirming the cosmological model, and the first detection of gravitational waves. There is something in common: the complete absence of surprise. What nature is confirming is simple: general relativity, quantum mechanics, and the Standard Model. Many physicists are looking for new theories by picking arbitrary hypotheses. I don't think this has ever produced good results. The clues we have are the successful theories and the data. What nature is confirming is that the next step may be only a question of combining them correctly. This is reassuring for loop quantum gravity, because these are its hypotheses. The primordial universe could open the window to predictions. It is filled with cosmic radiation, a sea of photons from the early hot phase. The details of this radiation tell us the history of the universe, and hidden in these details could be footprints of its quantum beginning. With more calculations and more precise measurements, it should be possible to test the theory. In 2013, Abhay Ashtekar, Ivan Agulo, and William Nelson published an article calculating that the statistical distribution of these fluctuations should reveal the effect of the initial bounce. The current data are not sufficient to evaluate whether they are correct, but measurements are getting more precise. Traces must also be in the gravitational field itself. There must be a cosmic gravitational background radiation, older even than the electromagnetic one. We have now observed gravitational waves directly with the LIGO detector. A more ambitious experiment, LISA, could see the primordial gravitational waves generated near the Big Bang. These waves should tell us about the quantum bounce. In the subtle irregularities of space, we should be able to find traces of events that took place 14 billion years ago. Black holes populate our universe in great number. They are regions where space is so curved as to collapse, and time comes to a standstill. They form when a star collapses. What enters a black hole does not come out again, at least if we neglect quantum theory. The surface of a black hole is the horizon. Close to it, time slows down. On the horizon itself, time stops. Black holes we observe are well described by Einstein's theory. But there are two mysteries that require quantum mechanics. The first concerns a fact discovered by Stephen Hawking. Black holes are hot. They emit heat, lose energy, and evaporate. Objects are hot because their microscopic constituents move. What are the atoms that vibrate, making a black hole hot? Loop theory provides an answer. The individual quanta of space on its surface. The heat is the result of their microscopic vibrations. It is possible to derive the formula for the heat of black holes foreseen by Hawking from the basic equations of loop quantum gravity. The second application is more spectacular. What happens to a collapsed star inside the black hole? General relativity predicts it is squashed into an infinitely small point. But with quantum gravity, there is a quantum repulsion, the same that makes the universe bounce. Matter gets squashed, but not to an infinitely small point. It bounces out. The bounce can be very fast, but seen from outside, it can take billions of years. After this time, we can see the black hole explode. A black hole is a shortcut to the distant future. Primordial black holes could be exploding today. Some have suggested that mysterious fast radio bursts could be signals from their explosions. If confirmed, it would be fantastic, a direct sign of a quantum gravitational phenomenon. When we take quantum gravity into account, the infinite compression of the universe at the Big Bang disappears. Quantum gravity is the discovery that no infinitely small point exists. The singularities predicted by general relativity are cured. The same happens at the center of black holes. There is another case where quantum gravity places a limit to the infinite concerning quantum field theory. The theory is full of mathematical absurdities called divergences. When we use it, we often obtain infinite results. These are eliminated with a Baroque procedure. Dirac was very unhappy with these infinities. They follow from the assumption of the infinite divisibility of space. When quantum gravity is taken into account, these infinities also disappear. The two theories, far from being contradictory, each offer the solution to the problems of the other. Putting a limit to infinity is a recurrent theme. Special relativity discovered a maximum velocity. Quantum mechanics discovered a maximum of information. Quantum gravity discovers a minimum length. The only truly infinite thing is our ignorance. We are approaching the conclusion of our journey. In this last part, I would like to return to the theory, but looking at its future, and to speak about information, a specter that is haunting theoretical physics. This chapter is different. If you have found the journey so far a little rough, hold on tighter. If this seems opaque, it's because my own ideas are confused. What is information? The scientific notion was defined by Claude Shannon in 1948. It is the measure of the number of possible alternatives. Information can be located somewhere. If you look at your ball and you know the color of mine, the colors are correlated. The world is a network of correlations between sets of atoms, a network of reciprocal information. The light arriving at our eyes has information about the objects it played across. A cell has information about the virus attacking it. The world is not just colliding atoms. It is a network of real, reciprocal information. This helps us understand heat. Heat is the random microscopic movement of molecules. A cup of hot tea cools down because the number of possible states of the molecules in hot tea and cold air is smaller than the number in cool tea and slightly warmer air. The combined state evolves from a situation with fewer possible states to one with more. Our missing information increases. Information cannot increase by itself. This is why entropy, or missing information, can only increase. Today, we accept that information can illuminate heat. More audacious is the idea that it can illuminate quantum mechanics. Quantum mechanics can be understood as the discovery that information in nature is always finite. The entire structure of the theory can be expressed in two postulates. 1. The relevant information in any physical system is finite. 2. You can always obtain new information on a physical system. The first characterizes granularity. The second, indeterminacy. Information reappears in quantum gravity. The area of any surface is determined by the spins of the loops that intersect it. These spins are discrete. A surface with a fixed area can be formed in many ways. If you know the area but not how its quanta are distributed, you have missing information. This is how we compute the heat of black holes. The amount of information depends on the area. When information enters a black hole, it is no longer recoverable. It appears as entropy associated with the area. But black holes evaporate. Where does the information end up? No one has a clear answer. This indicates we need to merge three ingredients: general relativity, quantum mechanics, and thermodynamics, or information theory. This brings us to the last idea: thermal time. The problem is simple. In fundamental physics, time plays no role. So how do we recover the notion of our everyday experience? Its origin may be similar to that of heat. It comes from averages of many microscopic variables. There is a link between time and temperature. All phenomena where we detect the passage of time are co-involved with heat. The salient characteristic of time is that it moves forwards, which means there are irreversible phenomena. Mechanical phenomena are reversible. When a stone hits the ground, it stops, and its energy heats the ground. At that moment, the process is irreversible. It is always heat that distinguishes the past from the future. The idea of thermal time reverses this. Instead of asking how time produces dissipation in heat, it asks how heat produces time. As long as we have a complete description of a system, all its variables are on the same footing. None acts as time. But as soon as we describe the system by means of averages, we have a preferred variable that functions like common time, a time along which heat is dissipated. Time is not fundamental. It appears because the world is immense and we are small systems interacting only with macroscopic variables. Time is an effect of our overlooking of the physical microstates of things. Time is our ignorance. Why does information play such a central role? Perhaps because we must not confuse what we know about a system with its absolute state. Knowledge is relational. The development of physics has shown that a vision of reality entirely independent of the observer is impossible. The world is a network of relations, of reciprocal information. We slice reality into objects, but reality is a variable flux, a wave, a mountain. These are not objects in themselves, but ways we have of slicing up the world to apprehend it. The same is true for all objects, including living organisms. A living organism is a system that continually reforms itself. Only those that are more efficient at doing so continue to exist. The effective way to persist is to manage information better. DNA, immune systems, sense organs, brains, languages, computers. They maximize the efficiency of information management. We are not atoms. We are orders in which atoms are arranged, capable of mirroring other atoms and ourselves. We are complex nodes in a rich web of reciprocal information. The truth is in the depths. I've described what I think is the nature of things. Am I sure about all this? I am not. One of the first and most beautiful pages in the history of science is in Plato's Phaedo, where Socrates explains the shape of the earth. He says he believes the earth is a sphere. He's basically right. He adds, I'm not sure. This acute awareness of our ignorance is the heart of scientific thinking. We are exploring at the borders of our knowledge. Science is born from this act of humility. The centuries in which people had faith in what they believed were the centuries in which little new was learned. Science is sometimes criticized for pretending to explain everything. As every researcher knows, doing science means coming up hard against the limits of your ignorance daily. A scientist is someone who lives immersed in the awareness of our deep ignorance. But if we are certain of nothing, how can we rely on science? The answer is simple. Science is not reliable because it provides certainty. It is reliable because it provides us with the best answers we have at present. Its answers are not definitive. They are the best available today because we don't consider them definitive, but see them as open to improvement. The nature of scientific thinking is critical, rebellious, and dissatisfied with a priori conceptions. The search for knowledge is not nourished by certainty. It is nourished by a radical distrust in certainty. This means not giving credence to those who say they are in possession of the truth. To accept the substantial uncertainty of our knowledge is to accept living immersed in ignorance and, therefore, in mystery. Ignorance can be scary. Out of fear, we can tell ourselves calming stories. For my part, I prefer to look our ignorance in the face, accept it, and seek to look just a bit further. Not just because this is the way to avoid superstitions, but because it seems to me to be the truest, most beautiful, and most honest way. The world is more extraordinary and profound than any of the fables told by our forefathers. I want to go and see it. To accept uncertainty doesn't detract from our sense of mystery. On the contrary, we are immersed in the mystery and the beauty of the world. The world, revealed by quantum gravity, is a new and strange one, still full of mystery, but coherent with its simple and clear beauty. It is a world which does not exist in space and does not develop in time. A world made up solely of interacting quantum fields, the swarming of which generates space, time, particles, waves.